Have you ever wondered how many different ways you can arrange your playlists? Maybe shuffle a deck of cards, or choose toppings for your pizza? Well, that's combinatorics, the art and science of counting possibilities when listing them all would take forever, as we have discussed in our previous video. Well, in today's video, we'll break down the rules of counting, permutations, combinations, and the principles behind them, so that by the end of this video, you'll see the hidden logic behind every what-if scenario in math. Also, we'll still focus on an intuition approach, then develop the formula afterwards so that it makes sense to you, as we did in our previous crash course videos. If you haven't seen that probability bootcamp yet, we suggest that you watch that video first, then come back to this video afterwards, because it sets you up for today's video. So today we're going to talk about combinatorics. What is combinatorics? It's a branch of mathematics that deals with counting and arranging. It asks questions like, how many ways can I arrange these items? Or how many selections can I make? Or how many possible outcomes are there? It's everywhere, from data science and probability to computer algorithms, cryptography, and even game design. So here's the fundamental counting principle. If you have m ways to do one thing and n ways to do another, then you have m times n ways to do both. In our last video, we called that our placeholder approach. And we did that kind of counting using multiplication in our probability bootcamp. For example, if we throw a regular die twice, what are the chances that the first throw is even and the second throw is odd? Well, as we showed last time, that's going to be 3 ways to plug the first placeholder and then another 3 ways to plug the second placeholder. And therefore, we came up with this probability, which is 9 out of 36. And we even showed you the visualization of the outcomes. Now, let's just focus on the counting part rather than the probability part. So we'll talk about permutations first, where order matters. Let's shift this time to using letters. How many ways can we order 3 letters A, B, and C in all sorts of ways without repetition? So using our placeholder approach, we have these 3 placeholders, and we have 3 ways to fill the first placeholder, 2 ways for the second placeholder, and only 1 way to fill up the last placeholder. So that means it's going to be 3 times 2 times 1. Listing them all up, we have these following arrangements. This means there are 6 ways to arrange 3 things at a time when order is important. Another example, how about if we have 4 letters A, B, C, and D? In how many ways can they be arranged in all sorts of ways without repetition? Again, using our placeholder approach, we have 4 placeholders, and we have 4 ways to fill up the first placeholder, 3 to fill up the second, 2 ways to fill up the third, and then just 1 way, the remaining letter they haven't used, for the last placeholder. Now, listing them all up is a bit harder this time, but it might help to list all the 6 ways to arrange 3 letters at a time and then just inserting D in all the possible places from start to end. For example, we're going to have this first line over here where the order will always be A, B, and C as you move from left to right, and then you just place the D in all the possible 4 places where you can find them. In this way, you're going to show 24 ways that this can be done. This means there are 24 ways to arrange 4 things at a time when order is important. Now, this kind of thing happens so much that an operator is introduced, the factorial notation excited number, the exclamation mark. So for example, if we have n exclamation mark, that simply means n times n minus 1 times n minus 2 times n minus 3 all the way to 2 all the way to 1. For example, in number 1, the answer is 3 times 2 times 1 or 3 factorial. For example, 2, the answer is 4 times 3 times 2 times 1, which is 4 factorial. Now, how about these 3 letters in example 1 We're going to use them, but this time we're only going to take them two at a time. But order is still important, meaning AB is different from BA. So if we're going to take them two at a time, then that means we only have two placeholders, and then we have three choices for the first placeholder, and then two choices for the remaining placeholder. So that gives you 3 times 2, and we're still left with 6. And this time, listing them, we have this arrangements AB, AC, BA, BC, CA, and CB. Right, let's move on. How about those same 4 letters in example 2? But we take them 2 at a time, but the order is still important. Therefore, we have 2 placeholders, and we have 4 choices. For the first placeholder, that means we only have 3 choices for the next placeholder. Therefore, that's going to be 4 times 3. It's equal to 12. And if we try to list them, it's going to be AB, AC, BA, BC, CA, CB, and AD, BD, CD, DA, DB, DC. Notice it actually gets quite hard to list down everything versus just computing for the numbers. So in example 1, the answer was 3 factorial. In example 2, the answer was 4 factorial. In example 3, however, we only have 2 placeholders instead of 3. Now, let's say we write it the way we just did it, but we're going to try to show some factorial notations. So instead of just having the 2 placeholders 3 times 2, we extend it all the way to 1 so that that becomes 3 factorial. And then we simply divide that by 1 factorial as well. It's a trivial exercise, but the answer will always going to be 3 factorial. So let's do the next example, number 4, where we had 2 placeholders and we have 4 choices. So again, we have 4 times 3. Now, to get a factorial notation, we might want to go all the way to times 2 times 1 and then divide that by 2 times 1 as well so that there's nothing changed. While the sense did not change, you'll notice that we now can write this in notation form 4 factorial all over 2 factorial, which is just like saying 4 factorial over 4 items minus 2 placeholders. The result would be you get that factorial. This means if you have m items taken n at a time, we will have m factorial over m minus n factorial. Now, this is the familiar permutation formula when m items are taken n at a time. But going back to our examples, we can simply think about m as the number of items that need to be arranged and n as the number of placeholders. For example, if we have 7 unique items taken 3 at a time, think of 3 placeholders and filling them with the 7 items. So we have 7 for the first choice, 6 for the second choice, 5 for the third choice, and that's it. However, so that we can achieve the factorial notation, we can multiply the numerator by 4 times 3 times 2 times 1 and simply divide that by 4 times 3 times 2 times 1. And although nothing has changed, it's still 7 times 6 times 5. We now have the formula 7 factorial over 4 factorial, which can be thought of as 7 factorial over 7 minus 3 factorial, the classic permutation formula. Now, you actually don't have to start the permutation formula when you're doing these kinds of problems. You simply can just go straight to our placeholder approach and do the computations directly. Do 7 times 6 times 5, and that's equal to 210 as well. There's no need actually to go back to the permutation formula if you know the basics. Still, the permutation formula is just a neat way of writing the formula down in factorial notation. But really, there's no real reason to resort to this if you're just working these simple kinds of problems. Besides, you can always use Excel and type the formula, and here it's going to be permute 7, 3, and that gives you 210 as well. How about combinations where order doesn't matter? So if order doesn't matter, then that means AB is the same as BA, and it should only be counted once, not twice. So if multiplying was the way to count the number of arrangements, then division must be required to reverse that count operation of arrangements. That means if three things can be arranged in 3 factorial, then it can be quote unquote deranged in 3 ways. Now let's revisit examples 3 and 4, but this time order is not important. This means we need to divide by the number of times the placeholders can be arranged, which is, I'll just call it placeholder factorial. So in how many ways can the letters A, B, and C can be arranged 2 at a time, but this time order is not important. So that's going to be 3 times 2 as before, but this time we have to divide by the number of ways 2 placeholders can be arranged, and that's just 2 factorial. So it's our old permutation formula, but we simply divide by the number of placeholders factorial, meaning the number of ways the placeholders can be arranged. In how many ways can 7 items be arranged 3 at a time where order is not important? So as before, that's going to be the 3 placeholders, or there's 7 ways to fill up the first, 6 ways to fill up the second, and 5 ways to fill up the third. And then we simply multiply by 4 factorial and then divide everything by 4 factorial so that we can get the way 7 items can be arranged 3 at a time where order is important. But since in this particular situation, order is not important, therefore we have to divide by the number of ways these 3 placeholders can be arranged. Therefore, we have to divide that by 3 factorial, and therefore we have this formula, and the answer is 35. Again, if you're solving this straight out, you can simply plug the numbers in the placeholders and take away the number of times the placeholders can be arranged instead of going through the above formula. And that will be more straightforward. So that's going to be 7 times 6 times 5 divided by 3 factorial, and still you're going to get 35. In Excel, you can type combin 7, 3, and you're going to get 35. Permutations with repetitions. When some items repeat, the number of unique arrangements is given by n factorial all over n1 factorial times n2 factorial, and so on and so forth, where n1 and n2 and what have you will be the number of repetitions of particular items. Note that we are simply taking out all the ways the repeated items can be arranged by dividing by the number of repeats, factorial, as discussed already previously, to reverse the overcounts in the multiplications. For example, the word level has 5 letters with 2 L's and 2 E's. Therefore, the number of ways this can be arranged would be 5 factorial over 2 factorial times 2 factorial, meaning the number of ways the repeat letters can be the range, or the arrangements can be uncounted. Combinatorics powers the modern world from passwords, encryption systems, decision trees, game theory, and strategy, for example. You might even want to try your chances of hitting the lottery by using combinatorics, and it'll help you understand just how much or how little your chances of winning are. But it's not impossible. You might want to try computing that using what you learned today in combinatorics. If you found this video helpful, hit like and subscribe for more videos like this. See you next time!